Yep. Hello, I'm Dongjae, and today I'm going to introduce Lilo, a higher-order relational concurrent separation logic for Liveness. This is joint work with these wonderful collaborators. Lilo is a concurrent separation logic for liveness, where liveness is a category of program properties that informally means good things eventually happen. For example, termination is a liveness property of a program. Then Lilo's main contribution is a promise mechanism for liveness reasoning, which combines well with existing concurrent separation logic techniques for safety, enabling verification of broader class of programs compared to previous work, as listed here. Although these are all interesting topics to discuss, I will refer you to the paper for concrete details. Instead, the goal of this talk is to build intuitions for our key contribution, the promise mechanism, so that this intuition can help you guide through the full details in the paper. I also briefly show you how we use promises to prove Lilo's triple specs. So let me introduce you a very simple example we will use in the talk called message passing, or MP in short. MP is a program with two threads where the left thread waits in a while loop for the right thread to write 1 to the memory location X. Here, our goal is to prove termination of MP, and to do so, let's start from the right thread, which we will call the writer from now on, and it's trivial that the writer terminates. Now let's look at the left thread, which we call the reader. This time we need to be a bit more careful because termination of the reader depends on the writer thread. In fact, we need to assume that the scheduler is fair, which means that every thread is always eventually scheduled. Then the writer will eventually write 1 to the memory, and the reader will read it and exit the loop to terminate. The most important observation here is that the reader depends on the writer for termination, and indeed, Lilo's promise mechanism enables precisely such reasoning to do liveness proofs. So to formally motivate the promise mechanism, let's review how we do safety proofs in concurrent separation logic using invariants. Our safety goal here is to show that the program never gets stuck, and we use this invariant for the proof, which I highlight using blue. We are using a point to predicate here, which means that we have some sort of permission or ownership to access this specific memory location. To be precise, the invariant says that the memory location X has the value 0 with half of the ownership, or has the value 1 with a read-only ownership. With this invariant, the proof is almost trivial. Let's first look at the writer, and we begin the proof with the other half of the points too, which we update to a read-only ownership when we update the memory, and this is enough to see that the writer never gets stuck. In fact, the reader's proof is even easier because when we need to read the memory, we can simply open the invariant and destruct the disjunction, and either of the two cases gives us points to with at least read permission, so we can safely execute the memory read, which is enough for the proof. Of course, we cannot use the previous proof to argue termination. This is essentially because the reader have no way to find out that the memory is eventually updated. Specifically, we need to rely on the fact that the memory location X is eventually updated to 1, but the invariant gives us only the disjunction. And Lilo's approach to address this issue is the promise mechanism, which enables us to express and rely on liveness guarantees of other threads. However, we cannot make promises for free because it would be unsound. To see this, consider a modification of the writer thread called no-writer, which omits the memory update. This thread is trivially safe, and not only that, we can use the exact same invariant to prove the safety of the reader. If no-writer can make a promise to update the memory, as the original writer thread would do, we are in a big trouble because no-writer never updates the memory and the reader never terminates, resulting in a completely different liveness property compared to the original MP program. Therefore, we must prevent such threads from making promises that they cannot fulfill, and this results in additional proof obligations to guarantee that threads eventually fulfill their promises. So, what is a promise? It's a Lilo predicate. That means that some thread T promised to establish a persistent predicate P, and I highlight it using orange. Then other threads can rely on this promise, and the thread T must guarantee that it eventually establishes the predicate. Then Lilo's proof rules involves the usual program logic, such as the points to predicates for memory accesses, and iris-style invariants, and rules for relying on and guaranteeing promises. I want to emphasize that Lilo's proofs are set local thanks to the promise mechanism. Now let's see how we use a promise to prove termination of the reader. Our proof is thread local, so we only need to look at the reader thread. Then we set up the exact same invariant which we used for the safety proof, and in addition, we begin the proof with a promise made by the writer thread to establish a read-only point 2 for the memory location X with the value 1. Note that we obtain this promise together with the invariant when we spawn the reader thread. Then we proceed as before, using the invariant to read from the memory for each iteration. However, this time we have the promise, and Lilo provides the promise rely rule that says we can eventually obtain the predicate that's been promised. So we eventually obtain the read-only points 2, and with this, we read the updated memory, we read the updated value and exit the loop and terminate. Now let's turn our attention to the writer thread, which must guarantee that it fulfills the promise. The intuition is simple. To guarantee a promise, a thread must fulfill it within some finite number of steps. However, we need to introduce 2 predicates and 2 rules to formalize this intuition. I'll first give informal descriptions and motivate them in the next slide. First, we have a thread private predicate called promise list, highlighted using red, which keeps a list of promises made by a thread. In the list, each entry is a pair of an identifier and the proposition that is promised. Also, we want to enforce each thread to fulfill all of its promises before terminating, so we have the empty rule. Then each promise starts with some finite number of progress credits, highlighted purple, and the text rule says that after a thread takes a step, it must submit 1 progress credit for all of its promises. Now, before we get to the proof of the writer thread, let's see how these rules prevent us from proving wrong threads that make promises that they cannot fulfill. First, let's revisit the no writer thread that omits the memory update. If we add a promise to this thread, we need 2 progress credits to proceed to the return instruction under the text rule. However, the empty rule prevents us from executing the return instruction because the promise list is not empty and our proof is stuck as it should be. Next, consider the delay writer, a thread that has an infinite loop before the memory update. If we add a promise to this thread, the text rule says that we must submit a progress credit for every iteration of the loop. However, no matter how many progress credits we start with, we will eventually run out of credits, and the text rule prevents us from taking any further steps from that point, and our proof gets stuck as it should be. As we can see from these examples, promise mechanism prevents us from proving wrong programs, and this is indeed the key to Lilo's soundness. Now let's do a step-by-step proof that shows that the writer thread indeed fulfills its promise. We have the proof state on the left, and the proof starts with the invariant, an empty promise list of the writer, and a half points to. Then before we spawn the writer thread, we need to use some rules to obtain some predicates. First, we use a promise add rule to add a promise to the writer and also obtain 2 promise credits from the rule. Then we use the promise get rule to obtain a promise predicate. And now we are done with pre-processing and we spawn the threads, feeding in the required predicates. Now we have the writer thread and execute the skip instruction. And because of the text rule, we need to submit 1 progress credit here. Then we execute the memory write and submit the remaining progress credit. In addition, we obtain the read-only points to predicate and use the promise fulfill rule to fulfill the promise and empty the promise list. Finally, we can execute the return instruction to terminate the thread. Because the promise list is empty, we can safely pass the empty rule and finish the proof. Now that I explained the intuition behind Lilo's promise mechanism, I'd like to show you how we can use promises to deal with more complicated cases. Specifically, I'll show you how we can define a triple specification for a ticket lock that guarantees termination. To begin, let's review a safety triple for the lock function, which says that if you acquire the lock, you get an exclusive ownership of the lock through the key token. However, this spec does not guarantee termination. In fact, the lock function guarantees termination only if any thread that acquires the lock eventually releases it. In Lilo, this condition is captured using the promise mechanism as we can see here. There's a lot of detail here, but let's focus on what's new compared to the safety triple. So this triple requires the promise list and a certain amount of progress credits as the precondition. These are required to handle client promises, and in particular, to respect the text rule inside the lock function. Then the post condition adds a new promise to unlock the lock in addition to the exclusive key token. This means that the thread must eventually unlock the lock, which is crucial for the termination of the lock function of other waiting threads. Of course, the triple for the unlock function needs to be augmented too. As one can see, a safety triple for the unlock simply returns the key token. However, Lilo's triple needs to handle client promises and the unlock promise. We handle the client promises in a similar way as the lock triple, and the unlock promise is fulfilled internally by the unlock function. I like to remark that the lock triples naturally prevent deadlocks because of the finiteness of the progress credits. This is summary of this talk. We introduced Lilo and its promise mechanism for liveness reasoning, which enable rely and guarantee reasoning for liveness. The paper has many more interesting details as listed on the slide, so please check it out. And thank you for listening to the talk, and I'll now take any questions.
Hey Dongjae, great work. The tax mechanism seems stronger than past work on termination, which used the ranking function. So you don't need to know when it terminates, you just need to show that some quantity decreases. Is that true? Is it stricter than ranking functions?
Great question. So I don't know much about the details of ranking function, but the progress credit mechanism is indeed quite a straightforward method to guarantee liveness in some sense, because you need to really show that there exists a finite number of steps. And I suppose it can be a bit more elementary than a more sophisticated method like ranking functions. But I don't know, maybe they share under the hood, they share some common theory or reasoning principle, but the rules indeed look different. But I don't know too much about ranking functions to really give a clear answer.
Yeah, I think there's something there. Thanks.
Yeah, we can chat offline.
Hi, great talk. It seems like it would be easy to construct a program where you have two threads where each of them is relying on the other for something like termination. Could you comment on how the promise mechanism would work in that kind of situation? Thank you so much.
Yep, great question. So the question is, what if there are two threads that rely on each other's promises? And so there is one inherent complexity that I didn't discuss in the talk, which is that there can be a cycle between promises, and we need to prevent cycles because it's unsound. And actually, the progress credit naturally rules out those potentially circular reasoning, because there are only finite number of progress credits that you start with, and it needs to somehow form a partial order. The amount of progress credits needs to form a partial order between promises that you can depend on. So yeah, the paper has much more details on that. So thank you.
One more question. Hi. Thank you for the talk. I have a more technical question. So in the paper, the progress credits is represented by a pair of numbers, where the first number is like a layer.
Yep.
I was wondering whether there's a need to extend that for say triples or progress credit with say more numbers.
Yes, great question. So in the paper, actually, the progress credit is not just natural number, but it's a pair of numbers that form lexicographical order. I didn't really discuss that detail here, but this pair is necessary because there can be some form of non-determinism in the program, and that might hinder us to straightforwardly count the line of steps in natural number. Of course, we can expand that. Actually, we can extend it to original numbers, not just triples or quadruples, but original numbers would probably be enough to, in general, enough. And yes, indeed, we can do that. We can also chat it offline.
Thank you.
All right, last chance to thank Stephen. Next speaker is Stephen Mell from UPenn, and he will be speaking about